Any one of you have to speak at least. Yeah, Anubhav?
Yes, sir.
Whether we have discussed the diagram intersymbol interference ಆಗುವಂಥದ್ದು, the signal distortion in fibers. ಡಿಸ್ಕಸ್ ಆಗಿತ್ತಾ ಇಲ್ವಾ? ಮರ್ತ್ಬಿಟ್ಟಿದ್ದೀನಿ ಅಂತೀರಾ? ಓಕೆ. If that is the case, anyhow, let me continue. So, so any phenomena in which the velocity of propagation of electromagnetic wave is wave independent. Dispersions. Okay. So, what is dispersion? Dispersion basically, uh, as you all know, due to the variation in the material property or due to the waveguide or due to the polarization mode that takes place in the fiber due to some other one thing, other variations, this dispersions takes place. So as you all know, whenever the light travels in a fiber using TIR principle, as I meant, while propagating to the medium, due to the variation in the characteristics of the signal, it is going to change. Change. That means the light gets dispersed. So some part of the incident light, while propagating, it gets into the cladding as well as few part will be spread in the core itself. Core itself. It is all due to the majorly three types. There are three different types. One is material dispersion, the other one is the waveguide dispersion, and the other one is polarization mode dispersion. So let us see what is this material and waveguide dispersion in detail. In detail. Before that, I wanted to tell you is this dispersion and this ISI. So what is this dispersion and ISI? So due to this dispersion, this ISI takes place. What is this ISI? So ISI is intersymbol interference. So in the first diagram, you can see the input pulse, which is been propagating. Okay, so here you can see separate pulses. See, you can see the pulses clearly at instant of time t1. For example, if you take time t1, you can see the pulses are clear, visible, and it is propagating. So as time proceeds, that is at time t2, t2 which is greater than t1. That means after t1. So initially at time t, the pulses are being fed. So later on at time two, you can see the same input pulse. It is being uh, the amplitude is being reduced and it is being propagated and it is being protected. So here the dotted line shows that it was supposed to touch this point and then it is to further proceed. And this point has to die somewhere. That means it has to check. So but there is a shift and it is moved. So later on, till as time permits, as time proceeds, sorry, as time proceeds, your signal propagates further with the symbol and interference. So here it was supposed to continue. Here it was supposed to. So here this gap. So this is what we call it as the intersymbol interference. So the pulses here gets interfered and the signal will be lost here. So this is at the time interval 3, which is greater than T1 and T2, both. Fine. Similarly, but it is the this one is distinguishable. You can make out it is exactly as the same way of same. But here you can see it is barely distinguishable. Not okay. Somewhat you can distinguish the pulses, but here as still time for proceeds. Here as distance is it proceeds further a certain distance. Again, here you can't distinguish since here large intersymbol interference takes place due to which a lot amount of information will be lost in this. So you know that any information. So for example, whatever may be the channel, the information capacity of this optical fiber during your digital transmission, it is usually specified by bandwidth distance project. So what is this bandwidth distance product? So bandwidth into the length in gigahertz kilometer. Okay. So the information carrying capability of your optical fiber is specified by bandwidth distance product, as you already studied in your previous classes. So for your multi-mode indexed fiber, this quantity is usually 20 megahertz kilometer for grid index fiber. So it is 2.5 gigahertz kilometer. And for single mode fibers, it will be larger than 10 gigahertz. Fine. So this dispersion, it is mainly due to three types. That is, one is a material dispersion, and the other one is a waveguide dispersion and polarization, as I discussed. So the group velocity. So this is these are all not there in your simply you can go through this. So the group velocity is given by Vg is equal to dw by d beta. The group delay is given by tau g because this all depends upon the propagation. hmm, It all depends upon this group velocity and group delay. So the group delay is given by tau g, which is equal to L by Vg. Vg is the group velocity. L is the length by this. So length into Vg is nothing but d beta dw by dw d beta. So it is given here. So you want to know that it all depends upon the frequency and the propagation constant. So omega is the frequency and beta is the propagation constant. In order to see the effects of this parameter on this group velocity and delay. Okay. So that is the you will see the input output characteristics. Already we know this. So at z equal to 0 and z equal to L. Okay. What is the input power? What is the output power? Here the optical signal waveform at the input of the fiber of length is f of t, optical signal. So the propagation constant is beta w, and here the output signal waveform will be g of t. So the input and the output they are related to this omega c minus delta d and w plus omega c plus delta omega into f of w into e power j omega t d omega. So it is again, why it is any function or any input function, it is represented using f of w into e power j omega t into d omega. Okay. Uh, as you all know, the sine wave or this. So similarly, the output it is minus jb because jb is what? jb is the jb is b is the propagation constant, right? So here omega t is the input signal and it is a propagation. So because in order to reach the output, it will some propagation delay. So that is the propagation into d omega. That is so here you can see the intramodal dispersion. So what is this intramodal dispersion and why it takes place? So as you all know, first of all, the intermodal delay and the intramodal dispersion. So the intermodal display, it is again we call it a modal delay. In the simple terms, we can say that it is a modal delay. The name is actually inter. So it is within. Okay, inter. Okay, that happens only in multi-mode fibers. So what in this mode here in this inner modal delay or a modal delay, it is caused due to here each mode because as we know it is multi-mode. Here each mode will be having a different value of your group velocity because you can see it in the group velocity. So different waves will be having a different okay different. Velocity at different at a single frequency so with which here we can derive an information carrying capacity of the multiple. That means here we can excuse different due to the different velocity here you can see. So there will be a delay within the fiber. That is what intermodal. So this is the intramodal dispersion. So this takes place in a single fiber. So this takes place in a single fiber, single mode fiber, single mode. Okay. Here the output will be proportional to the delayed version of the input signal, as we saw in the previous slide. In the previous slide, So the output is always proportional to the delayed version of it because it has to travel a particular distance. So that the propagation constant, right? So it has to travel through a certain distance to the group velocity of the wave. As your propagation constant is frequency dependent. By seeing the previous expressions, we had seen that it is frequency dependent over bandwidth delta W, sitting at the center frequency omega c. So if you take a sine wave like this, if you see, I think you can, for example, if I take this as a curve, this is a curve. If it is operating in a range, for example, only consider this one part of the sine wave. So if you consider, if you plot this as a emission wavelength versus relative output, for example, if you take x-axis as emission wavelength and y-axis as your relative output power, then here here you can see it will be spread across your window, second window or third window or whatever. So here, for example, if you consider as a second window, so here if it travels from 810 to around 1890. So it will be centered at 850, for example, if you consider 850, the peak wavelength will be around 850, for example, if you consider. Then so here you will be calculating FWHM. FWHM. What is this FWHM? So which all the calculations we are not teaching you, but to be for you to know, you should at least simply you know why they do calculate all those things. So full wave with half bandwidth. Okay, full wave with maximum with half FWHM. Full wave half minimum, sorry, half maximum. So it is FW FWHM. It is full wave at half minimum. Sorry, half maximum. Full wave at half maximum. So what we do, full wave at half maximum. So here you will take the line like this. Here you will be taking a line this. So this will be full wave. So here it is spread across 810 to 890 if it is. Then the maximum you will be taking only this part, the half. So here you will take 850. This is the half of this. Whatever the maximum from here to here, what is the maximum? That maximum you will take half. So you will be taking a line and you will be drawing a line vertically. So what is this gap? So this wavelength you will take. So that is what FWHM. So that FWHM it comes around 36 nanometer. 36 nanometer. So that wavelength they'll be using it. They using it. So there the spectral would be 36, which where the LED emits most of its light. So the LED here it emits in this particular range. So in this particular area, it will not be emitting much light, whereas it will be emitting most of the light in this particular wavelength. That is in this 36, 36 nanometer wavelength. So that's the reason here we'll be writing that diagram. So I think it is clear what that is. Why we take FWHM full wave at half minimum, so half maximum. Sorry, half maximum. So we'll be considering the half maximum. So that is so one constant present is specific. As the output signal is collectively represented by group velocity and group delay, this phenomenon is called as intramodal dispersion or group velocity dispersion. Another name. So here, this phenomena arises due to finite bandwidth. See, why finite bandwidth? Because it is FWHM. You will be considering the half maximum value. So that's why here this phenomena arises due to a finite bandwidth of the optical source, depending on the effective index of the wavelength and the modal dependency of the group velocity. So as it all mainly depends upon the frequency and the frequency and the propagation constant, right? Since it is dependent on frequency, means indirectly it is proportional to the wavelength also. So suppose if it is operating in a different window, then the FWHM will be different for the that window. So now if I consider it for our 810 to 890 or that waveform, So there the FWHM comes around 36 nanometer. Fine. Okay. In the case of optical pulse propagation down the fiber, this GVD is the group velocity dispersion. This causes pulse broadening. See, in the case of optical pulse propagation down the fiber, so as your optical wave, it propagates throughout the fiber. This group velocity dispersion or this intramodal dispersion, this causes the pulse broadening. So pulse broadening as a pulse, it broadens as it pulse broadens. That is what you can see here. Here the pulse is getting broadened as it travels over a distance, as it travels, due to which certain information will be lost. That is what here he says, which is leading to intersymbol interference. That's what. Here it is going, the pearls will be broadened. Here you can see the diagram figure. So this part you can see here. Here the distance you can see it is more. That means here the FWHM comes different. It will be more. So that means it will emit more light in more area, due to which spreading takes place. Spreading takes place. Here also you can see more FWHM comes. See here, it will be here. Half of this means it will come here. So here, so if you consider here some more area, if it is more area, then again the light will be spreading in that much area, due to which it is not confined to the particular place. Understood? So that is what it is leading to intersymbol interference. Next topic is material dispersion. So what is this material dispersion? As you all can see here, this is the fiber, general fiber, where you will be having core as well as cladding. So mainly this is arise due to the variation in the refractive index. See, here you can see that different lights are traveling at different wavelengths, and that will be given at the as the output, right? So it is all due to the variation in the refractiveness of the core material. It is a function of the wavelength. As you can see, wavelength versus the intensity. If you plot, you will be getting like this. Okay, the center frequency, not the center wavelength. Okay, yeah. And then okay, why I got disturbed is this Yuvraj Xavier. Nobody wants to join. Xavier just joined. Okay, Tanmay. ತನ್ಮಯ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಇರುವಂತಂದ್ರೆ ಟಾಪಿಕ್ ನೋಡ್ತಾ ಕೂತ್ಕೊಂಡು ಇದ್ ಮಾಡ್ತಿದ್ದೀರಾ ತನ್ಮಯ್ ಪೇಪರ್ ನೋಡ್ಬಿಟ್ಟು ಅದ್ರ ರಿಪ್ಲೈ ಮಾಡ್ತಿದ್ದೀರಾ ಕ್ಲಾಸ್ ಆದ್ಮೇಲೆ ಟೈಮ್ ಇರುತ್ತಲ್ವಾ
Sir, sorry, sir.
ಓಕೆ ಇಟ್ಸ್ ಓಕೆ ನೀವು ಮಧ್ಯದಲ್ಲಿ ಇದ್ರೆ ನಾನು ಇದ್ರಲ್ಲಿ ಇರ್ತೀನಲ್ವಾ ಮಧ್ಯೆ ನನಗೆ ಮೆಸೇಜಸ್ ಬಂದ್ರೆ ಐ ವಿಲ್ ಗೆಟ್ ಡಿಸ್ಟರ್ಬ್ ಇಟ್ಸ್ ಫೈನ್
Sir, ಅದಕ್ಕೆ ಮತ್ತೆ.
ಇಟ್ಸ್ ಫೈನ್ ಓಕೆ ತನ್ಮಯ್ ವಿಲ್ ಟಾಕ್ ಲೇಟರ್
Okay, okay, sir.
So in the here you can see the spectrum is spread across. Here the intensity is high, but the wavelength is very less. So here you can see it is being spread across. So this all these excitation sources are inherently non-monochromatic and emit within a spectrum. So here you, as you use the different wavelengths of this thing, so they will be not of single color only, as you all know. Okay, wave in this guide with different free space wavelengths travel at different group velocities due to the wavelength dependency of N1. So due to this refractive index, and again it is wavelength dependence. Since the material is different here compared to this cladding, so here the light it all depends upon the refractive index, and here the light will be traveling because of this different wavelength. As wavelength changes, but the speed will be same, but the group velocity will be changed. Okay, the waves arrive at the end of the fiber at different time, and hence result in a broadened output pulses. Okay, it is all due to the change in the different times, and hence it results in a broadened output wave of pulses. The material dispersion. So the refractive index of the material, it varies as a function of wavelength. You all know that we have already discussed. So material induced dispersion for a plane wave propagation in homogeneous medium of refractive index n, and that is given by dispersion tau max is equal to all these equations. You need not to worry about these equations. So as and when it is required, you can make use for a while if you are working with this. Okay, d mat of lambda is material dispersion. So how it will be dispersion takes place. You can see material dispersion diagram. See here the wavelength as wavelength. Yes. So it is a plot of the refractive index versus the wavelength. So it will be constant and later on there will be a change. So it is due to the variation in the index of refraction versus the wavelength. Wavelength. Okay. So this diagram tells you the material dispersion that takes place as a function of this wavelength versus the material dispersion. Okay, maybe the here you can see it is SiO2, that is silicon dioxide and germanium dioxide and silicon dioxide mixture. Both. Next comes waveguide dispersion. So what is this waveguide dispersion? So this waveguide dispersion, it is due to the dependency of the group velocity of the fundamental mode as well as the other modes on the V number. So this topic is not there in your syllabus. It's not there in your syllabus, but in the textbook in your textbook where case. So I'll not go through this, but simply for to tell you about this, I had taken this slide. So this waveguide dispersion. Again, here it all depends upon the mode number, V number. Okay. So in order to calculate a waveguide dispersion, we can calculate using this constant. Using this constant. Uh, so by solving this, we can calculate the propagation constant, and also using this V number, we can calculate this. Okay, this is all we are not to worry about, and we are not working on it. So the delay time, it is given in this waveguide dispersion. So it is in single mode fiber. So next comes here your polarization mode. So this is also one type of one reason due to which your dispersion takes place. So here you can see the input light pulses. And also, and earlier I think I had told you. So since it is just like a capacitor, you will be having a plate and in between, what is that? You'll be having in between. You can consider this optical fiber as a waveguide, right? Waveguide or similar to a parallel plate capacitor. How can you compare this your optical fiber as a capacitive fiber? Sorry, as a capacitor, parallel plate capacitor. Can anyone tell me? Can anyone tell me? Other day I think I had explained you. So what did I tell you that day? No answers. What is that in between? You'll be having. It will act as a waveguide, right? Hmm? If no answer, I think you can refer once again to the previous pages if you had noted down. Okay. So here I won't tell you once again. Here the core refractive index has different values along two orthogonal directions corresponding to the electric field oscillation directions. So here the polar here you can see hmm, it will be different. So we can take x-axis and y-axis along these directions. So an input light will travel along the fiber with ex and ey. So here the fields will be different as the field will be different in the different directions. So it will travel uh, along with the fiber with a different polarization because the field at x direction and the y direction will be different. It will be having a different group velocities. And as a group velocity, it is directly dependent and it is dependent upon the frequency. Here, as in travels, the output will be arriving at different times. Different, it will arrive since it is all depend upon the group velocity. It arrives at the output at different instance of time. Different instance of time with which there will be a delay. There will be a delay to that. There will be a delay to that. As a result, dispersion takes place. Okay. So again, this is effect of birefringence module. So I think birefringence that we are not study. So once we study there, the fourth chapter, we will be discussing that birefringence model. So there again, we will be talking about polarization dispersion, chromatic and total dispersion. All these things that we will discuss later. Okay. Afternoon. It's fine. So, ಇದು ಅನುಭವ್
Sir, yes, sir.
ಹಾ ಇದು ಸ್ಲೈಡ್ ತಗೊಂಡಿದ್ದೀರಾ ಅಟೆಂಡೆನ್ಸ್
Okay, thank you.